Hello everyone, I'm Karthik from ITA section and my roll number is 1230. Today on tech concept video, my topic is about algorithm optimality. Let us know what is algorithm optimality and what are its types in further slides briefly. I'm going to discuss about this algorithm optimality in further slides. Let us jump into our topic. Coming to the introduction, in computer science, an algorithm is said to be an asymptotically optimal if, roughly speaking, for large inputs it performs at worst a constant factor and independent of the input size and worse than the best possible algorithm. It is a term commonly encountered in the computer science research as a result widespread use of big O notation. So this is introduction about algorithm optimality and how it will be large inputs. It performs at worst constant factor and worse than the best possible algorithm. And it is a term commonly encountered in the computer science research as a result of widespread use of big O notation. So more formally, an algorithm is asymptotically optimal with respect to a particular resource if the problem has been proven to require phi of omega of f of n of that resource and the algorithm has been proved to use only big O of f of n. These proofs require an assumption of a particular model of computation, that is, certain restrictions on operations allowable with the input data. So this is about a brief notation about how the algorithm optimality will be and how it requires the resource and the algorithm to prove the use of the algorithm optimality. So these proofs are assumption to a particular model of computation and restrictions on operations allowable with the input data. Let us see a flow chart on this. So first, coming from the top, start initialize a population of particles, their positions randomly, and if no, we come directly is termination condition satisfied, or if yes, the evaluate the object function and update p best and the g best and update velocity and position of the each particle, and we come to this at is termination conditions satisfied and optimize if s the optimization finish and identify clustering method of the optimal solution and desired clustering method. This is a flowchart on algorithm and the optimality of this algorithm. So coming to algorithm, so let us know what is an algorithm. As simple example, it's known that all the comparison starts requires at least omega n log n comparison in the average and the worst cases. Coming to merge sort and heap sort are comparison sorts which performs big O of n log n and comparisons, so they are asymptotically optimal in this sense. So if the input data have some priori properties which can be exploited in construction of algorithms, in addition to comparisons, the asymptotically faster algorithms may be possible. So basically any algorithm, it knows all the comparison sorts requires at least omega n log n, but in comparisons in average and worst case, but the merge sort and heap sorts are comparison sorts which performs big O of n log n comparisons. So these are basically optimal in this sense, and if the input data have some priori properties which can exploited in construction of algorithms, in addition to comparisons, the asymptotically faster algorithms may be possible by using this. For example, if it is known that the n objects are integers from the range 1, n, then they may be sorted big O of n time. Example by the bucket sort. And a consequence of an algorithm being asymptotically optimal is that for large enough inputs, no algorithm can outperform it by more than a constant factor. So, if you take an example, for an objects are integers for the range from 1 to n, then they may be sorted of a big of n time. For basically we know the bucket sort, and a consequence of an algorithm being asymptotically optimal is that for large enough inputs, no algorithm can outperform if it by more than a constant factor. So, after knowing the algorithm, let us know what is optimality. For this reason, asymptotically optical algorithms are often seen as the end of the line in research. The attaining of a result that cannot be dramatically improved upon. Conversely, if an algorithm is not asymptotically optimal, this implies that as the input grows in size, an algorithm performs increasingly worse than the best possible algorithm. This is an optimality. Optimal algorithms are often seen as the end of the line in research, the attaining of a result that cannot be dramatically improved upon. Conversely, if an algorithm is not asymptotically optimal, this implies that as the input grows in size, and algorithms perform increasingly worse than the best possible algorithm. So, a consequence of an algorithm being asymptotically optimal is that for large enough inputs, no algorithm can outperform it by more than a constant factor. As we have discussed this point in the previous slides, that is earlier slides. For this reason, the asymptotically optical algorithms are often seen as the end of the line in research. The attaining of results that cannot be dramatically improved upon. Conversely, if an algorithm is not asymptotically optimal, this implies that as an input grows in size, the algorithms perform increasingly worse than the best possible algorithm. So, in practice, it's usual to find algorithms that perform better even if they do not enjoy any asymptotic advantage. New algorithms may also present advantages such as better performance on specific inputs, decreased use of a resource, or being simpler to describe and implement. Thus, asymptotically optimal algorithms are not always the end of the line. Although asymptotically optimal algorithms are important theoretically, results and asymptotically optimal algorithm might not be used in number of particle solutions. It only outperforms more commonly used methods for n beyond the range of particle input sizes, such as inputs with more bits than could fit in any computer storage system. It is too complex so that the difficulty of comprehending and implementing it correctly outweighs its potential benefit in the range of input sizes under consideration. So, this asymptotically optical algorithms are importantly theoretical results. It only outperforms more commonly used methods for n beyond range of particular input sizes, such as inputs with more bits that could fit in a computer storage system. It's too complex that the difficulty of comprehending and implementing if it correctly outweighs its potential benefit in range of input sizes and under consideration. The inputs encountered in practice fall into special cases that have more efficient algorithms, or that heuristic algorithms with bad worst case times can nevertheless solve efficiently. On modern computers, hardware optimization such as memory cache and parallel processing may be broken by an asymptotically optical algorithms assuming the analysis did not take this hardware optimization into account. In this case, there could be suboptimal algorithms that make better use of these features and outperform an optimal algorithm on a realistic data. An example of asymptotically optical algorithm not used in practice in Bernard-Chazelle linear time algorithm for triangulation of a simple polygon. Another is the resizable array data structure published in resizable arrays in optimal time and space, which can index in constant time but on many machines carries a heavy practical penalty compared it to ordinary array indexing. So this is about the algorithm optimality and asymptotical optimal. Thank you.